In a previous lesson, we saw how to use A/B testing to determine the better of two alternatives. We used the example of choosing between two different banner ad designs for a website, and a simple approach would be to try it out and test. For example, of the first 2,000 people to visit the website, we could randomly show 1,000 of them version A and the other 1,000 of them version B. We could then run a basic hypothesis test to see whether one is better than the other. But what if we have more alternatives? One approach is to just test each one of them, for example 1,000 times each, and then run a statistical test to compare the results. But there's another issue to consider. Each time we do one of the tests, we might be losing value. Let's say there were 10 different alternatives, and we tested each one 1,000 times, and number 1 turned out to be the best. So the 1,000 times we tested alternative number 1, we were showing the best ad. But the other 9,000 times, we were showing an ad that wasn't the best, so we probably lost value. Had we shown them number 1, we would have gotten more people clicking on our ad. And what if we hadn't stopped at 1,000 tests each, but had done 10,000 tests each? We could be more sure that number 1 really is the best ad, but we would have lost even more value from showing ads that weren't our best. So there's a trade-off. Every time we're presented with an opportunity to show an ad, we have to balance the benefits of getting more information and getting immediate value. In analytics jargon, those two types of benefits are called exploration and exploitation. Exploration means that we're focusing on getting more information, in this case to determine with more certainty which ad is really the best. And exploitation means that we're focusing on getting immediate value, in this example to show the ad that seems to be doing best so far because it seems to be most likely to be clicked. The question of exploration versus exploitation is somewhat common, especially in machine learning algorithms. In our context, there's even a name for this sort of problem, the multi-armed bandit problem. The name comes from gambling, specifically slot machines. In a slot machine, you put money into a slot and pull a lever, and depending on what pictures show up in the machine's window, you either win money or get nothing back. A slot machine is sometimes called a one-armed bandit. One-armed because of the lever that sticks out like an arm, and bandit because the probabilities of winning and the amounts you can win are carefully calibrated to give the player a negative expected value. On average, you'll lose money playing them. So that's a one-armed bandit. But suppose there were several slot machines next to each other, each with a different expected payout that we don't know. A slot machine player would want to play the one with the highest expected payout, but the only way to find out which has the highest payout is to test them all. Anyway, here's how the multi-armed bandit approach works. There are different variations, but they all work something like this. Suppose we're testing k alternatives. We start without any information, so each alternative seems to have equal probability of being best. So for the first test, we have an equal probability of selecting each alternative. After performing some tests, we've gotten more information, so we can update the probabilities of each one being best and start assigning new tests according to those probabilities. We keep testing multiple alternatives, so we're still doing exploration, but we make it more likely to pick the best ones, so we're also doing exploitation. We keep repeating this process, collect data, update probabilities, and continue until we're sufficiently sure which one of them is best. And along the way, we're getting more value out of the process by making it more likely to pick the options with higher estimated value. As usual, there are several parameters we can vary in this sort of algorithm. We can change the number of tests between recalculating probabilities. We can change the way we update the probabilities. For example, we can use Bayesian updates or estimate from the observed distributions. And we can change how we assign new tests. For example, just looking at probabilities of each alternative being best, or taking into account the expected value of each. And also, as usual, there's no simple rule for what choices will work best, but in any case, it usually works much better than running a fixed large number of tests for every alternative. And it's worthwhile. Multi-armed bandit models both help you learn faster on the fly and also create more value along the way.